so we omitted them. In the upper panel, we see the original network, and we see progression of a fast variant with a minimum time to infect that is lower than each interaction the time. So the pathogen can take every possible path along the network. So there is a probability to get infected in every interaction. On the lower panel, we see a slower variant. So not all interactions are infectious. The probability there would be really, really small because there will be less than the minimum time to infect. Individual outcomes can predict the load on hospitals, beds, and the number of deceased, if any. And as you can see, when the network is highly dynamic and we have a very fast pathogen, even when the population is young, there's going to be quite a lot of load on hospitals. Do that. We further wanted to inspect asymptomatic infection in the population. So we ran the simulation over the CNS dataset while varying the average age of the population. So you can see here we have 10% asymptomatic, and here the population is really, really young. But we see no effect. On the y-axis is the rate of infection. So we see no effect. And it was weird, because we know that there is an effect. But one thing that we have noticed is that the CNS network is very dense. Every day, the temporal density is about 0.2, which means 20% of all possible interactions between these 700 students are happening every day. So we wanted to reduce temporal density, so we split each day into 2 or 3 pseudo days, each containing half or a third of the interactions of the original day. So for example, a network with half the density will be represented as twice as long in terms of pseudo days. We then repeated the experiment, varying the percentage of symptomatic and asymptomatic individuals in the populations over the longer, less dense networks. In sparse networks, we observe a significant effect of latent asymptomatic transmission. Symptomatic individuals in sparse networks do not infect many before isolating. However, asymptomatic individuals continue interacting and spreading the infection. Thus, asymptomatic transmission influences the total infection rate primarily in sparse networks. Our model can project the individual probability of getting infected on an average day as a function of the number of exposures and their aggregated duration, accounting for varying level of personal vulnerability, which is different than the susceptibility. Vulnerability here takes into, this is a P max value, and it depends on factors such as immunization, inoculation history, and age, comorbidity situations, etc. The higher the vulnerability, the greater the risk during each exposure. We also analyze here the fastest variant, assuming it can cause infection in every encounter, regardless of duration. Our findings indicate that recovered or vaccinated individuals have a significantly lower probability of infection compared to others with similar levels of exposure. Okay. We then wanted to continue and use the model to evaluate the effectiveness of various social distancing methods. Spatial distancing, for example, correspond to social distancing pods that's separating the population to subgroups that can meet. Temporal social distancing involves a pure dilation of the timeline while preserving individual activity potential, and thus prolonging the time of interaction. And spatial temporal distancing pertains to the situation in which fixed subgroups of the overall group meet at alternate times. We had that in Israel, where schools classes were halved, and every half of class would go on alternating days. We also try to analyze how robust the strategy is by considering the phase of the disease progression in the community. In an early phase, there is a small number of initial patients. If the disease has progressed in the community or there was a super spreader event, we have larger number of initial patients. Okay. We start with social distancing pods, the spatial pods, using our synthetic temporal networks. So we start with the initial configuration of 1,000 nodes and 10,000 snapshots. We created sequences of these subgraphs of size defined by the required split. So here you see this is the original network. Here it is split to 2. So we recreated it a bit like in Gil's talk, and then recreated and recreated the situation. On the left, we have with 2 initial patients assigned randomly, and here we have 10 initial patients assigned randomly. We can see that social distancing pods are effective only at the early stages of the disease, when there are just a few isolated cases. For example, after a super spreader event, social distancing pods will probably be less affected. We can see here that the majority of the population is infected. Okay. Here we examine the effect of timeline dilation. Timeline dilation is what I explained before, the stretching of the timeline. For example, consider a conference in which we maintain all planned meetings and gatherings, but spread them over more days, such that in every day we have half or third of the original planned interactions. Here we use the CNS real-world data set. So, on the upper panel, we see the original network. Here with 1 initial patient, and here with 6 initial patients. We repeated every experiment 200 times. Here we see stretched networks where we created pseudo days of 12 hours and sort of had more days. We just cut the simulation so it will look alike. So we see that dilated timeline lowers the ability of pathogens to infect, as infected people have fewer opportunities to infect before they are removed. For example, a pathogen that spreads to over 75% of the population in the original network would infect less than 50% of the community in the dilated network. The result is robust when the number of initial patients is high. We also wanted to see how different pathogens behave in the same community. So what we have here is, again, the infection rate, and here is the delay, the minimal delay that the pathogen needs in order to infect. And this is on the original network, and this is on the dilated timeline network. We are more interested in the range of, we call these slow pathogens because 60 to 70 seconds to infect is quite a lot. These are paths that are actually completely almost non-existent in the network. So we find, as can be seen on the upper panel, that slow spreading pathogens spread roughly at the same rate as fast spreading ones in highly active communities. It's surprising since the pathogens may follow different paths. However, the dilation of timeline considerably slows the spread of the slower pathogens, as you can see here. So we have less. Lastly, as SARS-CoV-2 continued to mutate, some of its variants became variants of concern. These variants either differ in their transmissibility, infectivity, pathogenicity, or their ability to evade immunity. We consider here competing conditions for 2 variants over our path-preserving random temporal networks, with different level of cross-immunity. Cross-immunity refers to the immunity gained against one pathogen that provides partial or full immunity against another one. We evaluate the infection probability of two variants here, slower and faster, changing the cross-immunity slowly. Each of these combinations was iterated 30 times to a total of 12,000 times for this heat map. The results were normalized to the range. The heat map shows that in the majority of the cases, the fast variant is the dominant one, with the ratio more than on the blue scale, right? So the blue, most of it is blue. When there is no cross-immunity between the variants, that is, a person can be reinfected with a variant after recovering from the other, both variants manage to reinfect the entire population. And you can see that in the upper left side here. Okay. We have other results for 3 variants, but I didn't want to overload this talk. So in summary, we find that the temporal dynamics of a community have a more significant effect on the spread of the disease than the characteristics of the spreading process of the virus. Hence, reducing the rate of daily interactions is a robust strategy. When considering airborne diseases, it is important to consider the duration of temporal meetings to model the spread of pathogens in a population. Lastly, we see that the enigmatic nature of asymptomatic transmission stems from the latent effect of the network density and has a substantial impact only in sparse communities. And these QR codes here are for the papers that I presented. Again, I want to thank my collaborators, Alex Abi, Yanir Marmor, and Yuval Shachar, and thank you very much.
So thank you. So we have some time if you have certain questions, and
It was very clear.
some question, discussion. Oh, yeah.
Thank you very much, Yossi, for the great talk. So my question is that the temporal networks are usually provided as a kind of a sequence of data in which diseases may or may not be happening. But in the real pandemic scenarios, people do respond to the epidemiological states of themselves. So have you, come up with any framework how to include that kind of behavioral response to the disease state, which is separate from what you did?
Right.
But yeah, this is more like a general question. Yeah.
Yeah. So we can assume a probability of going out, right? Yeah. So that would be the more sparse networks. But we have seen that in sparser networks, asymptomatic people actually infect a lot. We know the story of the guy who lived in the north of the country, came to the high-tech company every 2 days, and in every one of his visits, another group of people were infected. But he was asymptomatic. Yeah. Thank you.
So any other questions? It seems no questions. So thank you, Professor
Thank you
Asnat.
very much.
Okay, so next speaker, Professor Sorrentino, please. Yeah, since we have some time, since there is no parallel session, so he can start little early, also 5 minutes early, so it's not a problem, I think. We can have more time for discussion at the end. Yeah, so please you can start. You can have another 5 minutes extra, so that's good.
Okay, thank you for attending the talk. And the subject of this talk is synchronization, which is a topic that I've been studying for some time. And as you can see from my title, thank you. The subject of the talk is efficiency of the synchronization dynamics in networks. And so let's introduce the topic of synchronization. I'm sure you guys have heard about it, but the idea is that there are many systems in nature, biological systems, technological systems, social systems that can synchronize. And these systems are always typically described by individual oscillators. They are coupled through the connections of a network. And a lot of the research in the area, including some of my work, has to do with the stability of the synchronous solution, meaning whether this synchronous state is a possible state of the network is stable or not against perturbations. Whether you start from a random initial condition or an initial condition in a certain part of phase space, and you converge or you don't converge to the synchronous solution. Clearly, this is a very important study, a very important subject of investigation, because if the synchronous solution is unstable, you will never see it. However, not as much research has been spent on investigating the efficiency of the synchronization dynamics, which I argue is an equally important subject because all systems in nature, but also technological systems, they must operate efficiently. And so we're trying to shift the focus from stability to efficiency, but the two things appear to be closely related. So the approach here is to introduce a new concept. It's the concept of the transverse reactivity. By transverse, we mean that it's transverse to the synchronization manifold. And we go beyond the classical concept of the Lyapunov exponents that have been studied, that have been used for many years to study the stability of the synchronous solution. It's including all of my work, or my previous work. I've always focused on these Lyapunov exponents. We try to go beyond the concepts of the Lyapunov exponents. And in terms of efficiency, here we consider two types of efficiency: energy efficiency and coupling efficiency, but these definitions are open. And most likely, you may come up with alternative definitions that are possibly more relevant to a certain type of systems that are not the ones that I'm describing today. So, but I really think the point that I want to make is that it is important to introduce a concept of efficiency, whatever that concept is. So it's open for different definitions. We can introduce different definitions, but at the same time, it's important to define efficiency of the synchronization process. How efficient is this process? And so what is this reactivity? So it's a pretty interesting concept. And the idea here is that you have let's talk about the simple dynamical systems that we can think about, linear time invariant. So X is the state of the system, and it has this structure, X dot, the derivative of X with respect to time equal AX. Now, the matrix A has all negative real part eigenvalues. That means that this system is asymptotically stable, meaning if you consider the dynamics for t that goes to infinity, X goes to 0. But the eigenvalues of A don't convey information on the transient dynamics. And so here we have two systems in the figure, one which we call non-reactive and one which is reactive. So the two systems are both asymptotically stable. They all go to 0 asymptotically, but the reactive system shows an overshoot. That's an engineering term. a growth in the state, in the transient, that you don't see in the non-reactive system. So the reactivity is another phase, another aspect of the dynamics that is non-asymptotic, and especially, so what does it measure? It measures the largest rate of increase of the norm of x instantaneously. And what does this reactivity, how can we measure it? Well, the reactivity is the largest eigenvalue of the symmetric part of A. So while the largest eigenvalue, largest real part eigenvalue of A determines the asymptotic stability, this reactivity gives you an idea that is the symmetric part of A, okay, not A, gives you an idea of the transient let me use system stability. And so, for example, I'm an engineering professor. We go and teach second-order oscillators. There are the over-damped oscillator, under-damped oscillators. I don't know if you heard about this. The whole theory of second-order oscillators that are the ones that are critically damped over that could be reintroduced in terms of reactivity. We don't do that because we like to work with the Laplace transforms. But it's the same idea, right? That there is an overshoot, a transient overshoot when the system is reactive. That would be the case of the under-damped oscillator. And so let's talk about synchronization. So synchronization, I'm sure you've seen these equations. There is xi is the state of an oscillator, the oscillator I, and there is an individual dynamics, there is f of xi, and then there is connections and an exchange of information between oscillators that are coupled through the connections of a network. The network connectivity is given by the matrix A, also called the adjacency matrix, but it's also given by the Laplacian matrix, which is a function of the adjacency matrix. The scalar sigma is typically taken to be positive quantity, and it's just some way to either amplify or reduce the strength of the coupling over all the network links. You can think it as a parameter that if you increase it, all the connections become stronger. If you decrease it, all the connections become weaker. And so, as I said, there are two different objects here, two different matrices. The adjacency matrix is the one that we're all familiar with. The Laplacian matrix we're also, almost all of us are familiar with. Just another way to write it. But it has some important properties. Especially the spectrum of this Laplacian matrix has the property that all the eigenvalues have negative real parts, and there is one eigenvalue that is equal to 0. And if there is a spanning tree in this network, then the one eigenvalue equal to 0 is unique. There is only one eigenvalue equal to 0. And as you can probably understand here, we're considering, I'm particularly interested in directed networks rather than undirected networks. And so the next step is the classical problem to study the stability of the synchronous solution. We can show that for this network with Laplacian coupling, there exists a synchronous solution where x1 is equal to x2 is equal to xn. We call that synchronous solution xs, and xs obeys the same equation as a single uncoupled oscillator. And about this synchronous solution, we can consider small perturbations, and we can study how these small perturbations evolve in time. If the small perturbation decay, then we have stability. If the small perturbation increase, then we have an unstable synchronous solution. And the method that I'm presenting here today to study stability of the synchronous solution is the classical method of the mass stability function introduced by Pecora and Carroll. And this method has the advantage that it decouples the stability problem into a number of independent modes. Each mode is independent of the other ones, and each individual mode can be studied independently of the other ones. And if all the Lyapunov exponents of these modes are negative, then we have a condition for stability. But let me be a little bit more precise. So what are these Lyapunov exponents? So these provide a Lyapunov exponents, give you a measure of the tendency of systems to synchronize through this mass stability function approach. And when we have a positive maximum Lyapunov exponent, that means that we have a perturbation that is growing asymptotically. And when we have a negative Lyapunov exponent, it means that we have a perturbation that is decaying asymptotically. And in order for the synchronous solution to be stable, all the transverse Lyapunov exponents must be negative. However, these Lyapunov exponents don't tell us much about the transient dynamics. That information is not contained. And I'm arguing here that a more complete characterization of the stability problem should take also into account the transient dynamics, and that can be done through the concept of the transverse reactivity. And so here is an example of mass stability function. Mass stability function is just a function that we can compute numerically and can provide information on the stability of many different networks. And what were we plotting here? We're plotting the maximum Lyapunov exponent of an individual mode as a function of this parameter sigma lambda. Remember that lambdas are the eigenvalues of the Laplacian. And so if you look at this specific example that I'm showing here, we have two transitions. There's a first transition that we call from asynchronous to synchronous, A to S, here. As you increase sigma lambda, you go from a positive Lyapunov exponent to a negative Lyapunov exponent. And then there is another transition that we call synchronous to asynchronous. As you increase sigma lambda, you go from stability to instability, meaning negative to positive Lyapunov exponent. Okay, and so that means that there are two critical sigmas here. There is a sigma critical for corresponding to the first transition, sigma AS, asynchronous to synchronous, and then there is another critical sigma, sigma SA, from synchronous to asynchronous. Okay, so if you imagine that you fix a network topology and you increase sigma, you first have a transition where the network synchronizes, then you have, for a larger value of sigma, you have a transition where the network loses synchronization. But now we're interested in the transverse reactivity, and so we're going to take a slightly different approach. In a slightly different approach, we're going to write down the same stability problem that we had seen before, and then we apply a transformation that doesn't decouple all the modes from one another, but only decouples the parallel motion from the transverse motion. Once we do that, we obtain a transverse, we call it this L-perp. There's a transverse version of the Laplacian matrix. That L-perp is important because it characterizes the linearized dynamics transverse to the manifold. And at this point, we're going to consider the reactivity of the L-perp equation, not of the full equation. That is this equation, okay? We're going to study the reactivity. But the reactivity depends, different from the Lyapunov exponent, the reactivity depends on the specific point on the synchronous attractor, which we call XS, on which we are. So we can imagine that you have a system that oscillates, let's say it's a limit cycle. Along this limit cycle, there are different points. Each point has its own reactivity. It's not a function of the entire attractor like the Lyapunov exponents. So we can have a positive reactivity at certain points, and we can have a negative reactivity at other points. And here there is another important step. In this equation for the reactivity, we study the reactivity of XS, we can extract out of this equation an important parameter which we call Xi, and Xi is the largest eigenvalue of the symmetric part of L-perp. This largest eigenvalue of the symmetric part of L-perp is something that people in graph theory have been studying for many years, and it is called the algebraic connectivity of the network. It's not lambda 2. Okay, lambda 2 works for undirected networks. This works for directed networks. But it's something that you can find in the literature. And when are these two quantities, when is this psi equal to lambda 2? Well, when the Laplacian is normal. And of course, a classical, an important case of normal matrices is symmetric matrices, which means undirected topologies. But here, we don't want to study, we're not going to focus on undirected topologies. We want to study directed topologies. And for those, typically, psi is different from lambda 2, actually is larger. And so this leads to this slide. Okay, here you see the attractor of the Lorentz oscillator. And for each point of the attractor, we're showing with different colors the transverse reactivity. Transverse reactivity is larger in the red region and is lower in the blue region. That means each point on the attractor is going to have a different transverse reactivity. And we can also divide the attractor into two large regions. One non-reactive region that is shown in green on the right, and one reactive region that is shown in magenta also on the right. Okay, so it's a little bit different from the Lyapunov exponents, because the Lyapunov exponents, there is that Oshedalek theorem and ergodicity, and then it becomes a property of the attractor. But this is not a property of the attractor. Each point has its own reactivity. And so now we can also define a worst-case probability that you randomly select a point from this attractor, and you are in the reactive region. In principle, if you want stability, you don't want to be in the reactive region. You wish to work with with a case in which the green region is large and the magenta region is small, but that can vary, and can vary from network to network and from oscillator to oscillator. So, so we can compute this number, okay, just a number that tells you how likely you are to be in the reactive region of the attractor. And here is an important concept that now, if we want, let's say we have two networks and we want to compare them. Is it just okay to compare the two psi's, meaning the two algebraic connectivities? And my answer is no. We don't want to just compare the psi's. And the reason is that we want to compare networks that have kind of the same asymptotic dynamics. And so in order to do that, we need to rescale sigma, the coupling, the sigma coupling that I showed you at the beginning of this talk, by lambda 2. So that leads to a new definition of reactivity, which we call sync reactivity. And this is the capital psi, you see, is equal to psi divided by lambda 2. Okay, so this sync reactivity is a purely topological parameter. You can come to me, you give me a network, you say, give me this sync reactivity index, and I can give you the number. Or you come and you give me another network, I compute a different number. It has only to do with the structure and not so much with the dynamics. And so we were able to compute this capital psi, the sync reactivity index, for different real networks. These are all directed, okay, and from the literature. And we see that there is some interesting patterns here that emerge. We're plotting the sync reactivity versus the real part of lambda 2. So in principle, you would like to be in an area where the sync reactivity is small and the real part of lambda 2 is large in absolute value. And that is the case of the neural networks. Neural networks seem to be good, synchronizable, both asymptotically and transiently. Okay, psi is a measure, topological measure of a network to synchronize transiently, and lambda 2 is it provides a measure to synchronize asymptotically. While, for example, the metabolic networks are the opposite. Okay, so this is some people may think that neural networks are designed to synchronize, and metabolic networks have not been favored by evolution in a way, and not been structured by evolution to be synchronizable, either transiently or asymptotically. And then here, I come to this other concept, that is the concept of efficiency. And as I said, here each one of us can come up with a specific measure of efficiency of the synchronization dynamics. And we came up with these two. One is the energy, the synchronization energy of the synchronization dynamics. Another one has to do with the coupling efficiency, meaning how large the coupling need to be compared to the AS or S to A coupling, critical coupling that I showed you in my original slide. And so we can see, at least this provides some idea about efficiency in this, according to these two definitions. And we see that this measure, at least in our experiments, this efficiency is related to the reactivity. So here is an example of how this actually works. So on the left, we're fixing the network. You see the network in A is given. It has its own syncretivity, but we pick two initial conditions. One initial condition is bad, is from the red region. Another initial condition is good, is on the green region. And you can see, eventually, the synchronization error that is plotted on the y-axis will go to 0, but you can see how the transient is dramatically different between the two initial conditions. On the right, instead, the initial condition is given, it's the same, but the networks are different. We have a network that is this unidirectional chain that is highly reactive, and then we have another network that is a unidirectional star, outgoing star, that has lower reactivity. So you can see also in this case how the transient dynamics is quite different if you pick the two different networks, and you see these transient peaks in the case of the unidirectional chain, but you don't see them in the other case. And so this led us to think about a synchronization strategy that would be efficient. And what is our synchronization strategy in a nutshell? Well, we're not going to spend the coupling as we typically do uniformly in time. We're only going to apply the coupling in the reactive region, in the red region. And we're going to use a much lower coupling, possibly even zero coupling, in the green region. And we hope that this will lead to a saving in energy and a saving in coupling. And this is our proposed strategy for sigma. You see sigma of t, and it can be parameterized in terms of these two parameters, beta and gamma. Okay, I'm not going into the details because I don't have time. And here is an example with the Lorentz system. So you can see we're comparing the two cases, the case on top, where sigma is equal to an average sigma and is constant in time, and the case in blue, and the case in red, where sigma is a function of time and is adjusted according to our proposed efficient strategy. And as you can see, there is an advantage both in terms of synchronization. We're varying sigma bar. So sigma bar is kept constant in both cases. Sigma bar is the average coupling expenditure. We're keeping the coupling expenditure the same. It's just that we're applying it at different times so that in the blue case, it's only applied when needed. And in the red case, it's applied uniformly in time. And especially what is interesting to see is this calligraphic E here, and you can see that that is the energy expenditure. The energy expenditure is by orders of magnitude lower, even though both the network synchronization is achieved, but the energy expenditure in certain ranges of sigma bar is by orders of magnitude lower when you apply our efficient coupling when needed strategy. And this is another example for the Rossler where we have the two transitions, the A to S and the S to A. I'm not going to talk about this. Finally, I want to just briefly describe this one. Here we are showing instead the coupling efficiency, not the energy efficiency. And so we're varying those two parameters, beta and gamma, when we are in the blue region, it means that we're spending 1% of the coupling, and we're synchronizing the network. While if you see 100, that 100 number, that means the coupling is the same. So if we apply the strategy, we can synchronize, and we are in this blue region, with this specific choice of beta and gamma, we can achieve synchronization by spending 1% of the coupling. I'm going to skip this, so I'm going to come to the conclusions. And so we're trying to move away from the Lyapunov exponents and try to characterize the transient stability as well as the asymptotic stability. And we are understanding that if you look at the transient, different regions of an attractor or a synchronous attractor have different properties. They're not all the same. There are good regions and bad regions. We can take advantage of that. So we can design coupling strategies, control strategies that are aware of the reactivity of different points along the attractor. Our work is especially relevant in the case of directed networks, and so non-normal matrices. And by designing a simple, very simple synchronization strategy that is aware of the reactivity, we can synchronize networks efficiently. Thank you.
Yeah, thank you. Thanks for some questions.
Thank you for your talk. Possibly it's a pedantic question, but in several of your formula, you have the algebraic connectivity in the denominator of the formula. The algebraic connectivity for the directed graph could be equal to 0, even if the graph is connected. So it's defined as the minimization of the Rayleigh-Ritz quadratic form. So I suppose that you should exclude this kind of graph. For instance, when you have a source in the graph, you have 0 there, and then you have on definitions there.
You are correct. We are only considering networks that have a directed spanning tree. So that will ensure that lambda 2 is positive.
Yeah, hello. So my question is, I didn't get what do you exactly do to transient dynamics to calculate the exact efficiency? Like you check the transient dynamics of any network, but what is the exact calculation that is going on that gives you how efficiently the network is synchronizing?
Well, there are 2 steps. The first step is to compute the reactivity. Okay, that is a measure of instability locally of each individual point along the attractor. So you need to look at an attractor, and you need to kind of apply some partition methods to define the positive and negative regions where the reactivity is positive and negative. Second step, we design an efficient coupling strategy where the coupling is applied, the larger coupling is applied in the regions where the reactivity is positive, and a smaller coupling is applied when the reactivity is negative.
So you check the positive and negative things to like get the efficiency per se.
Yeah, in other words, if let's say the reactivity is negative, okay, that means you don't need to do anything. The dynamics will go spontaneously to 0. Okay, but if the reactivity is positive, or maybe you need to apply very small coupling. If the reactivity is strong, then that's when you need to come in and apply strong coupling so that you prevent the growth of the perturbation.
This is irrespective of how long the transient dynamics is, right?
You will do it for all the time that it takes.
Okay, thanks.
Yeah, one more.
Thank you, Francesco, for the fantastic talk. I will ask you about the thing that once the system is connected, the nodes are no longer in the original attractor.
When the system is connected,
the nodes are no longer following the original attractor. They are pushed out of the attractor. Then I wonder how they still react to the transfer reactivity of the original attractor where they are no longer there.
Okay. Thank you for the question. So all that we're doing here, everything that we're doing here is localized, is local about the synchronization manifold. So we're not getting away from the manifold. But you're totally right. If the system is reactive, even if the Lyapunov exponent is negative, okay, the Lyapunov exponent means that this infinitesimal perturbation will go to 0. Effectively, in the transient, the perturbation may grow. You may possibly leave the basin of attraction, and you can have, in practice, the system becomes unstable, even with a negative Lyapunov exponent. And that's a different story. Here, all we're doing here, we are assuming that we're staying close to the manifold, close enough that we're not going to see that. But you have a good point, and and so that leads to a question that that I'm very interested in, and that's the question of the basin of attraction.
Okay, so any questions? No. Okay. Thanks again, Professor Sorrentino. Thanks again. So now this is the tea time, and then